All right, so you guys can see the screen. Okay, yeah, I think I won't turn on my video because the connection is not so good. So I just not want to risk it. Or let's see, I'll turn it on, and if there is a problem, I'll turn it off. Because it's just good to have the video on a little bit. Already this is online and so on. So it's a little more real, maybe. Yeah. Okay. So I wanted to discuss, maybe let's discuss the first question of the test, because there is something interesting there, which I want to discuss because we have not done that thing, but let's see. Okay. So, so what was the first problem? So this is problem 1. So problem 1 of just problem 1. Yeah. So anybody just remembers the problem? Yeah. So basically, we wanted to see for what matrices, or rather for what dimensions, right? For what n and m is it possible to make an array such that, so someone please say the condition. Every row and column has exactly 1, 1. Is that right? Good. Okay. Right. So every row and column has let's say exactly 1, 1. Good. Yeah. So let me explain this question a little bit, because so what I'm saying is that for what arrays, for what, it's not just arrays, but like for what choice of length and breadth is it possible to make an array so that every row and column has exactly 1, 1. So very silly, but for 1 by 3, is it possible? Is it possible? So if you have a 1 by 3 grid to begin with, I mean, so you're only going to put zeros and ones, right? Only zeros and ones, nothing else. Yeah, it is. Yeah, it is certainly not possible, right? Because yeah, there are 3 columns, and so how is it possible? So then that's when, so you guys understand the question. So Ishana, do you understand the question, right? So for which MNN will it be possible? So someone, yeah, please say. Even guess for what kind of N and M do you think it will be possible? You can even just say some numbers. You don't have to say like, but some numbers. Like, is it possible for a 2 by 3? So a priori, there are several ways to do it. So that's why we have to give some explanation. So if I make a 2 by 3 grid, then is it possible to fill this with zeros and ones so that every row I want only 1, 1, and every column also I want only 1, 1? So who said it first? Give the explanation. So why should there be 3 ones? Because columns, right? Yes, exactly. Yeah. So you can just say that 2 rows, or you can say counting along the rows gives me 2 ones, right? But counting along the columns give me 3 ones, right? So 2 rows implies 2 ones. Yeah. But 3 columns imply 3 ones. But how is this possible? So does everybody see the idea, right? This is the first problem in what is called double counting. Yeah. You count something in two different ways and then you make a contradiction or something, or you get some. Yes. Yeah. So everybody understands for 2 by 3 it is not possible. I think I'm just saying same thing again and again. Yeah. So let's come to 3. So 3 by 3 it is certainly possible. So everybody agrees. Someone doesn't agree. Yeah. For 3 by 3 it is certainly possible. So remember, you're only going to fill this with zeros and ones. I don't know what happened. You're only going to fill this with zeros and ones. And so you can fill it like this. Yeah. Yeah. So what is the general answer? Someone please say a general answer. Now I don't want numbers. Yes, so that's Aparna, you were saying same thing. Yes, n and n equal to m is just, that's all. That's the only condition. Under no other, I mean, under no other case is it possible. And it's a very simple question. Okay. So now let me give some extensions of this question. And these are important. These are not just puzzles. Okay, this will be important questions later on, because, so let's not think about because now, but let's just see the question. Now the question is, given n, how many such arrays are there? Given a n, okay, how many this is a very important question for later, and it's just a good problem for now. Yeah, such that every row and every column is exactly one. Yeah. So can you just answer this for this 3 by 3 case for me? I'll just come in a minute. Okay, I'll just wash my face. Okay. Okay. So we are looking at variants. So sorry. So some can anybody find, yeah, others? Okay, so you have found 3. So can you just give me one more so that others get idea about, yeah, if they don't have. First column, no, I didn't understand. Okay, like this. Huh? Okay. Okay, so there's one more. Okay, so don't tell the other not needed the other, but this is okay. So build on this. Maybe others can give the complete more. Yeah, Nagesh, you were saying. No, yeah, that's right. In the initial question, I don't say that maybe, but it doesn't matter. The zeros don't matter in the initial question, okay? But to answer this question, it should be zeros and ones. Is it fine? Considering all that, but then you see, even if you consider all the digits, the answer to the first original question does not change. Right? Does everybody agree, right? So because the other digits don't really matter, we just counted the ones and so. And for this question, I mean, you can put other digits, but again, that will be a simple extension. One can work that out. But the more important question is this. This is a very important question you will see later on. Okay. Okay, so we have two. So seems like there are more. So anyone has, I want someone else now. Let's see if they can find something else. Sorry. You found two more. Okay. Right. So can you tell the logic, or is it just by? So can you say that if there is any logic or? Mm-hmm. Okay. No, but for the second column, there are two choices, right? Either you can, so basically you can just say where you're going to put the one. That is, yeah. So either you can put the one here or you can put the one here, right? So everybody sees this, right? If you fix the first column like the way we have fixed, and the second column has two choices, but then the third column is completely determined. That is another important thing. These are the elements. These are the elements, okay? So one way to look at the question. And how many choices are there for the first column? 3. Yeah. So here it is, right? It's a good old step-by-step counting that gives the answer. And what is it? That you go column wise, go row wise, doesn't matter. So we go column wise. Okay. So maybe just let me say this in details. Okay. So for column 1, it's okay to write C1. For C1, yeah, we have 3 choices. Yeah, you can put the one here, you can put the one here, you can put them. Once again, you see the other digits, even if we do that variation, are not very hard. Okay. So for 3 choices for the first column. And once you make that choice, no matter what choice you make, but once you make that choice, then there are 2 choices for the second column. Yeah. After this, for C2, we have 2 choices for each of the 3 choices, right? For each of above, right? I mean, if you make this choice, then you have either there or here. Yeah, if you make this again, either here or here, but yeah, they'll give you different matrices. And the third column is fixed. So the answer should be 3 by 2, or 3 into 2. 3 times 2, that is 6. Is it? Yeah, is everybody following? Unab? Yeah, Pragdish, is it fine, everybody? Good. So you see, this is yeah, we'll see this, how important this is. So if you have a 4 by 4, then what will the answer be? Hmm? If it's a 4 factorial, right? And that's where the factorials come in. And you would not have seen this in, it's not a standard, I mean, whatever that means, but this is very important. Okay, this is the right way to look at permutation, says algebra. Okay, like the theory of permutations, how many problems you can solve with just that logic, it's fine, but want to do more matrices are important. Okay, so that's what we will. That's how this will be useful later. So we have 4. Then again, you can see there are 4 factorial, or 4 into 3 into 2, right? And similarly, so this is the very good problem. Okay. Now I want to give another variation which I'll not discuss now. Okay, which you can do homework. These are very good problems, counting problems, and yeah. So that problem is there. I should see. Given n, how many arrays such that every row and every column has even number of ones, and this is again a 0, 1 matrix. Okay, so you should keep this in mind. Has even number of ones. One minute. Yeah, this can be done for n comma m, but fine, we'll just do for n by n. Has even number of ones. Okay, we'll not discuss this now. Note this down. Okay. Then I want to discuss another problem related to this, which is similar to the initial question we had. Okay. All right. Has even number of ones. So every row should have even number of ones, and others will be 0. If n is odd, then there will be odd number of zeros. Yeah. If n is even, then even number of zeros. Now we want to look at another variation. This also turns out to be useful later, but it's a good problem. Then let me just say this title first. So arrays with every row and column having at least okay. We want to look at these kind of things. Okay, now we don't want exactly or anything, but every row and column should have at least one. Okay, so yeah, okay, just a minute. Okay, so yeah, all right. So the question, I was going to note down something. So the question is here. So for what m and n, for what m and n, yeah, is it so possible to have, so let me call these kind of arrays regular arrays. I'm just calling them regular. Okay, those arrays in which every row and every column has at least a 1, I'm calling them regular arrays. Okay, so the question is for what, so for what m and n is it possible to have no 1 minute, no, for is it possible, so for what m and n Yes, but that is not the question. Yeah, you can just put all ones. Yeah, but that's not the question. The question is, for what M and N, so that's what I'm trying to frame. For what M and N will, for what M and N is every regular array reducible? And let me describe what I mean by reducible. So don't get panicked if you are, don't get panicked by the word reducible. Okay, I'll just describe. So I'm asking for what M and N is the following can happen. That you have a regular array. Obviously, you have regular arrays for every M and N, but every regular array you take, you should be able to delete a row and a column so that the resulting smaller array is also regular. That's what I mean by reducible. Yeah, you should be able to delete a row and a column so that the resulting array is again regular. Okay, for which MNN can you do this? Yeah, so let me give you an example. If I give you a, let's take the same thing. Yeah, if we take a 1/3 array, 1/3, yeah, palette, and then we fill this. So let's say that I give you this. So this is certainly regular. Is it regular? Yeah, every row and every column has a 1. But then, is it reducible? Is it reducible? So here we are not going to delete rows, for example. Let's forget about the rows here because only one row. Is it reducible? It is reducible, right? Because you can delete, you can in fact delete any column, right? So you can delete this column, right? You're deleting one column. So you're able to delete a column so that the resulting thing is still regular. You see, the resulting thing is still regular. Okay. You delete this and you remove it, attach, it is still regular. Whatever rows and whatever row and columns are there, they each of them have at least a 1. So it is reducible. So this is fine. No, at least a 1, but it's a 0-1 matrix, but there is no condition on zeros. I mean, in the sense that you may not have zeros, but you don't have anything other than zeros and ones. Okay. Yeah. So there is, yeah, but let's not consider the one by anything case. That's a little, because you cannot delete a row, in fact. Yeah. So let's forget about that for it. Let's just take a 2 by 2 thing, 2 case. Let's take a 2 by 2 case. So first question, is this regular? Yes. Is it reducible? Why? Yes. Yeah. So what is the row and the column? No, but you have to remove a row also. So reducible means you have to remove one row and one column. Everybody sees this definition, right? You should be able to remove a row and a column so that the resulting thing is still regular. Second. So not the first row, you see. If you remove the first row, then that's bad. But you remove the second row, then the resulting thing is just this, which is regular. Yeah. So the definition is, should be able to reduce some row and some column. Okay, I'm not writing it. Yeah, fine. So this is reducible. Yes, so there are several ways. Yeah, there is another way. So If you remove the first row and first column, then also, and these are the two ways. Yeah. Yes, that's indeed correct. Yeah. So you see, so if so, you take any, in fact, it seems like, I mean, you can check it. Is this, so is this regular? It's not even regular, right? So there's nothing to, it's not regular. The second row doesn't have a 1. But the point is that, I mean, you take any, I mean, any regular matrix, any 2 by 2 regular matrix is reducible. Does it seem to be true? Just asking for the 2 by 2 case. Yeah. So can you can you give an explanation? Yes, it seems like we can always leave a 1. We can always leave a 1, but any other explanation if you would? Yeah, it's sort of almost obvious. Yeah. Okay. So when you have a 1 and everything is a corner, so you can leave that corner. And so is this making sense with everyone, the definitions? Yeah. What does it mean for something to be regular? What does it mean to be reducible? Okay. So so that's important here. Any 2 by 2 regular matrix is reducible. So 2 and 2 work. Okay. So anyone has problems? This? Yeah, you should interrupt me and ask, because this is interesting, but only if you understand the language. Otherwise, it can get confusing. Okay? Now the question is for 3 by 3. So this laptop is so. Cha. So you're saying any regular matrix will be reducible. Okay. So okay. So if you have an so it's the answer seems to be yes. Yeah. Some way you're saying yes. Still a question mark. Oh no, but you may not end up with a regular matrix. That is the whole point. I mean, you have to make sure you remove a row and a column so that the resulting 2 by 2 thing has a 1 and has a 1 in every row and every column, right? Right. So for example, if you take this, no, I mean, it's correct. And conclusion, okay, I don't know, we'll check. The conclusion may be correct, but the point is that if you remove things in the wrong way, then it's not going to work, right? For instance, if I remove this and this, then what do I get? First one to be clear about that. What do we get? So just for this particular, so I'm not saying that again, this is not reducible, but I'm just doing a bad deletion. So that's why it seems. So, but we can wisely reduce it to, but it's not like we're going to use a 2 by 2 because once you remove, because the whole question is to get a 2 by 2 regular matrix. Now further reduction is not being asked. That is also possible, obviously, from what we have proved, but that's not being asked. But you see, this does not work. So can anybody give a good reduction of this? A good reduction? Yeah. Everybody sees this? This is a good reduction. Okay, good reduction. Okay. Now the claim is, yeah, that this you can do this for any 3 by 3 irregular matrix. Good question, right? It's a good combinatorics question. I mean, as you can see, this was also, as you can kind of imagine. I mean, if you have sense, if you have means if you have seen, if you have a sense for this thing, if you have seen it, and it's likely, otherwise it's difficult to imagine, is that this can be useful in induction, because certain thing has a certain property, and you are, if you prove this lemma that you can reduce it and still have that property, then you can apply induction on it and get it. And this lemma was used in a very big kind of, some PhD thesis of someone. Okay, this simple lemma, obviously this was just 2 lines in that 80-page thing, but this lemma was a key to proving some algebraic thing, very deep thing. But this is a very good combinatorics question. And let's see. So and in fact, that was later used in some computer science thing, some automata thing, I believe. Yeah. So how do we show that any 3 by 3 matrix can be reduced? That is really the question. We need to reason with any, or you can also do some sort of casework if you like. So see, we have already said that there are only 6, not regular, but there are only 6 matrices which have exactly 1, 1 in every row and every column, right? If you can explicitly show it for all those 6, then are we done? Because any other 3 by 3 matrix will have more ones. Will have not just more, but a superset of ones. Do you agree? Yeah. Everybody sees this, right? So we have said that there are 6 of these good matrices. Yeah. So there are 6 matrices. So like this one, and then there are others, 6 of them. And if you can show, and I'm sure you guys can show, right? So you just write down those 6. I mean, that's what you can do if you're not getting any ideas, right? You see those 6 one and try to reduce each of them. And you will see that you will be able to reduce them. Then for any other regular matrix, it will sort of contain this matrix, right? There will be ones in superset of places, right? Because every row and every column must have at least 1, 1 to begin with. So it will be built up from these. And so it will be done. But then you cannot use this method because, I mean, that also grows fast, right? 4 factorial, 5 factorial. You can't really check it. So then how do you give a good reasoning? In fact, it is very simple. It's a very, it's a very simple thing. So let me just explain it for n by n. So it's fine. This is a slightly new idea. So, but then I'll ask some variations which you guys can try for homework. I mean, the idea is that you have to just figure out which column you can afford to delete. Right? So I agree that we have to delete 1 row and 1 column, right? But you can just focus on deleting a column first. So, I mean, in general, if you have, so just a few more lines. So that we just say, Okay. This now you see 5 by 5 or 6 by 6, 6 by 6. Okay. So what will I do? Well, I will just go row wise. Just traverse the rows. You want, so the goal is to be able to delete one row and one column, right? So just go row wise. Yeah. You go to every row and ask where is your one, at least one, right? So you go to the first row and ask for where is your one. Well, it is there, right? Somewhere. Let's say that it is here. Then I go to the second one and I ask, where is your one? He says, well, it is here. It could be in the same column, no problem. I go again to the next row and I ask, where is your one? Well, it's here, let's say. And then I go to this row and I ask, okay. So, well, what happened? 1, 2, 3, 4, 5. This is 6. It even looks wrong initially. So that's why I got confused. I don't know what happened. Yeah. Then you go to the next row and ask, where is your one? I say, let's say here. It says here. Okay. You see what is happening. I go to the 5 rows, and let's not go to the 6th row. Yeah, because I need to delete one of them. I go to the 5 rows and I ask, where are your ones? They report their ones. Now, obviously, how many columns can we use? We cannot use more than 5 columns. Yeah. In this process, we cannot use more than 5 columns. Everybody agrees? So then, can we not delete that column? At least one of them. Yeah. We can delete this column, right? Because it doesn't affect, yeah, the rest of the 5 rows are, and we can delete the last row. Now, okay. So yeah, now it's okay, right? That every row and every column, because well, this column will also have a, but the problem is that where is on the beginning meaning? Fifth column. No. So it was a regular matrix to begin with. Do you see? So, I mean, right? I mean, we are starting with a regular matrix and we are seeing if we can reduce it. Is it fine? Yes. Yeah, this is not a regular matrix because I have not yeah, that's right. So I should complete it first. So let's say that this is here, this is here, and so on. Fine. So that has 2 ones. So I can put 2 ones, doesn't matter. But let's say I put this, and this column also. Let's say it has a 1 here. No problem. Right. So now it is regular. Yeah. So I mean, and my point is that yeah, it was regular. I was marking the ones that I kind of receive in the process. But yeah, initially I should say that it started with a regular matrix. And I went from row to row, and so let's go to all the rows. I went from row to row and I asked them, where are your ones? Okay. Right. So now, but then there is a problem, right? I mean, what if one minute? Is something is wrong? But can we reduce it? So let's see. Okay. So just 1 minute. So maybe, so that might be some ad hoc way. That's but 1 minute. So there's a 1 here, 1 here, and 1 here. Yeah, certainly. Yeah, that's right. Well, I don't have a problem with that. But just a minute. Yeah, so there is no problem. Yeah, no problem. That's right. Yeah. So the point is that here, But I'm just going to give a general explanation, right? So the general, obviously you guys can figure out, I mean, you can see that there are reductions here, but general explanation should be there. So you go row by row, right? And you ask, where are your ones? Yeah. But then in general, how would you make the reduction? That is really what the question is. Yeah. So you see, you go to the first 5 rows. Yeah. If you go to the first 5 rows, then you will end up using 5 columns. Right. And you will not use one of the columns. Then the thing is, can I remove that column which I don't use? Is it okay to remove the column which I don't use? Will I still have a regular matrix? You guys see? So I go row by row and I ask the columns, I ask where are your ones, and we mark them in their columns. If we forget about the last row, then we leave that. The last row has a 1, right? I mean, so, or let's say the last row has a column, but the first 5 rows will use some 5 columns or 4 less than that columns. Yeah. Then I can, so I can remove this column which was not used. Is it okay to do that? Yeah. But then if I remove this column, then I can also remove this row. Is it okay to do that? Okay. But what if, but the question now comes, what if, so if you're going to remove both a row and a column, then the problem can come in somewhere in this case, where both those unused columns had their ones in the last row. Then you cannot just delete that row. You see? Yeah. So like in this particular case, yeah, if so we may end up with 2 unused columns. Yeah, when we make the row traversal and I ask every row, where is your 1? So I use at most 5 columns in the first 5 rows. I may end up not using 2 columns, right? Then, but then I can say, okay, I don't use those 2 columns and then don't use the last row, I can remove the last row. But the problem is if I remove the last row and one of those columns, both, then I may have a problem in like in this figure. If I remove this row also, if I remove the last row also, you see the resulting matrix? Yeah, it won't, yeah, right? It may not be regular because the rest of these things might be 0. Everybody sees the problem, right? You can remove a column, but you can't remove a row and a column at the same time, like so easily at least. Is it fine with everyone? You see the problem? Yeah, Nagesh, do you see this? Yeah, okay. So, but at least we can remove a column. Yeah, at least we can remove a column. So at least we can remove this column. Yeah. Yeah, it seems, but then is that even correct to do? First, then we can solve it after. No, but you want to only remove 1 row and 1 column, right? We don't want to remove through 3 and so on, right? Reducible means that 1 row and 1 column. You are only allowed to remove 1 row and 1 column, right? Not more than that. Okay. So that is the thing. So you see, in this case, we will not do both the things at the same time. We cannot do both the things at the same time. So what we will just do in this case first is we will just remove this column, not the whole thing, not the last row. So obviously not the part that intersects this column with the last row. We cannot remove that, right? Because you're not, as we said, we cannot remove both row and the column simultaneously. That gives a problem. Okay, but at least we are able to remove a column. Now you will see that you come to a 5x6 case. Everybody sees, right? You come to a 5x6 case, or rather 6x5 case. Yeah, once we do that, at least we can say, right, that you are in a 6x5 case, which is regular. Be careful, I have not been able to do both row and column at the same time, because it doesn't, yeah. We don't know, okay? But at least we come to a 6x5 case. And from here, we will try to wisely remove some row. And you can feel that it can be done, right? Just how I removed a column, I can now remove some row. It will not be the last row necessarily, but I can. Because now I'm in a 6x5 case, which is also regular. And if you copy this example, let me just put the one in the last row, just to emphasize that. There was a problem if we would have removed the last row also, yeah. So, but let's just draw this figure. So there are some steps to this. Yeah, it's not a very direct thing, but it's, I think, interesting. And then we have 3. Okay. And so now you have so basically you should keep in mind that you have a regular 6x5 matrix. So basically you have an extra row. That's all. So that, wait, so wait, 1 minute. So then something is wrong, right? I mean, if I remove that, oh, I'm doing something wrong. So what did I say earlier? That if I remove this column, but if I remove this column, then I have to remove this one, right? I mean, there is no other way, isn't it? I mean, I have to remove that one, obviously. So then what's going wrong? Yeah. Yeah, that is certainly there. I agree with that is there. But then, no, but then the problem is that then this matrix, I have to reason that this is also regular. 1 second. So how do you find a way out of this? So, well, we can say like this, you see. So I have to remove this entire, first of all, there is no way out of it, right? I have to remove this entire thing. I have to remove this entire column. I mean, it was stupid to say that I cannot remove that particular one. Okay, I remove this entire column. Okay, now you see, the point is this: if this row, there are two cases, right? If this row has, another one, then I am fine. Yeah, then I can move on. Yeah, but if this row does not have any other one, this row does not have any other one, then it means that this one is not here, but then it means that this one is there in some other row. For this particular column, the one is there in some other row, in which case I can remove also this row. You see, so there are two cases, right? Yeah. So I mean, either okay. So the point was this, right? So you remove this column, so you certainly have to remove this column. I mean, certainly we are trying to remove this column. Now, are we going to remove that row? In this figure, you should not remove that row. Yeah. In this particular case, let's just see. We should not remove that row, because you see, if you remove that row, then the fourth column has a problem, right? So this is the game, and this row and this one. In this case, it's fine. I cannot remove the last row. I have to go to a 6x5 case, and then I have to think. Okay, but what if what if the situation was like this? And someone tell me, what should we have done in this case? So forget about this figure for now. If the situation was like this, then what should we have done? Certainly I'm removing this column. Let's say that is we do. Then what else should I do? What row should I remove? In this case, last row, right? If this is the case, then you certainly have to remove the last row. And then you're done again. So then you don't even have to go to the next case. You get a 5 by 5 matrix, it's regular. Yeah, and this reasoning is not based on the rest of the entries, so it is fine, right? Okay, so basically you find the column which was unused, you remove that column, and then you remove that last row if the last row doesn't have any zero, it doesn't have any other one, which means that for the other columns, the ones are there above, and so there are no problem. And if there's a problem, then you come to this case. If there is a problem, means that, you know, if there is this one here, then you cannot remove the last row, then you come to this case. And now it's a homework, try to show that for 6 by 5 also you can do like this. So what the question is that for, and it's not hard to guess how, right? For similar method will work, right? So for any 6 by 5 matrix, regular matrix. So I will not use the word reducible now, regular matrix, because for any 6 by 5 regular matrix, we can remove a column. I'm not saying row. Okay. I mean, that is possibly also true, but I'm just saying, so that is that true? That I think is not true, but at least this is true, right? We can remove a row and still keep it regular. Not hard to guess. How? So for any 6 by 5 regular matrix, so you see there's an extra row, right? So there is an extra row means you can remove that row, right? So you basically have to go column wise, right? You go column wise and you ask every column. Yeah, you ask this column, you know, where is your one? He says here. You ask this column, where is your one? Here. Yeah, and then you go to this column and you see the one. And then you go to all the columns, right? But then in this way, when you go to all the columns, I mean, one of the rows will not be used. And you can certainly remove that row because I mean, every other columns has their ones, right? In the other rows, right? And so every column will have a one and every row also has a one. Yeah, because we have not removed, I mean, because yeah, those ones were found in those rows. Yeah. So you see, and but still try to write it. So it's a two-step game, right? I mean, you cannot do it directly, maybe because you cannot guess both the rows and the columns, but it is possible. Okay. So what we have shown is that every square matrix is reducible. You can remove a row and a column. Okay, that's important. It's not like just a row, but we are removing a row and a column. Okay, so first we are removing the column and then removing a row, but well, you see, it doesn't change, right? I mean, you understand, right? So in this particular question itself, you could have removed this, then this, and you understand, right? And you would have got the same answer, but we didn't get it directly. But yeah, in looking back, you can just say, yeah. So is it good? Yeah, it's fine. Yeah, this is a rather unique, I mean, it's very simple, but I just don't, it's a good thing. So it's a new, different thing. So it's good to discuss these things because this is not, because the more non-standard yet, I mean, keeping in the, yeah, things you do, it's better. The standard things are already there and do. But yeah, this is just a problem, interesting problem. Okay. Now you see, so what we have shown is that any 6 by 5, say you can take a row. And similarly, so let me write this. Point is that, I mean, from, so from any n comma n plus 1, a column can be removed for any from any regular n comma n plus 1. Mean basically think, right? If you have an extra column, then you can certainly remove a column, right? If you have extra column, then you can remove a column and you can still have a regular matrix. Yeah, for any column, a column can be removed. Right? And as we have just seen, if you have an extra row from any regular, and I've described the process very elementary, it's very clean, it's a very simple process. Yeah. In a row can be removed. Yeah, fine. But then you see, it's very interesting because this from here, if you remove a column, then you end up with an n cross n case, n cross n regular. But I mean, just now we have seen that from an n cross n case, a row can be removed. I mean, see, in an n cross n case, I have shown you how a column can be removed. Just a column. We have seen both, but we have also seen that a column can be removed. From a square case, a column can be removed. But in the same way, from a square case, a row can be removed. Just to the same argument, right? I'm not asking for both. Both can also be done, but one can also be done. But the point is that you can combine them. And so from n cross n regular, yeah, a row can be removed. What does it amount to? So from here, you will get a n minus 1 cross n. Yeah, regular. What is the total amount? It means that even from this is the fantastic thing, right? Even from this, you can remove a row and a column. That's what you're ending up doing. Is it okay? Because see, first I can remove a column because there is an extra column, that reasoning we have seen. But then if you have a square, then you can remove a row, just like I removed a column from a square. So overall, you can remove a row and a column. I mean, a column and a row, same thing. Even from this kind of matrices, you can remove a row and a column. So when the difference between the row and similarly n cross n plus 1 cross n, you can do just, I mean, it's just, you don't have to do, just take same thing. Yeah. See, so even when there is just one extra, if there is one extra thing, if there is one extra column or one extra row, then also such removals can be done. Okay, that you can remove a row and a column. Fine. So what you can do for homework is you can try to, just draw and just try to just take 2 by 3, 4 by 5, and you just draw it. Just ask someone to draw, just make a thing and you try to reduce it. Okay, and you see you can do both a row and a column. It may not be trivial to reduce it sometimes, but you can reduce it. Fine. Any questions? So you have to work this. That we have already seen, like just now, that you can, yeah, so that case also we have seen, right? That case we saw first, yeah, like a 6 by 6, yeah, as you saw, we first remove the column and then we remove the row, some row. It's possible. But this is also possible. When one row and column is extra, then also it can be done by using the square case, right? By making a square, right? Yes, yeah, but you cannot reduce any other to this case because we are only asking to remove one row or one column. not more than that, right? So n cross n, so this thing you cannot reduce it directly, right? So I mean, if you have this, then certainly it is clear that a column can be removed. Same reasoning, right? Extra column, a column can be removed, right? So then you end up like this, right? But then from this, it is not necessary that a row can be removed. Is it necessary that you can remove a row? Yeah, not necessary. Can anybody give an example? So I'm only asking for a row. Don't remove both a row and a column from 2 by 3. So if you take 2 by 3, obviously we cannot remove a row sometimes, or we can, let's see. No, we cannot, right? So if you draw a figure, so if you draw, yeah. So which row are you going to remove? You cannot remove any row. If you remove the first row, then the first column doesn't have a 1, right? If you remove the second row, then it's worse. First and second column don't have a 1. So the logic is very simple, right? When you have less rows, you cannot remove them. Yeah, whatever is more, then you can remove. And we have, but that one has to give a reason which we have given. And in square case, you can remove both, or you can remove one, which was useful. Okay. So this is the thing, you see. So basically for this kind of, so for n cross n, for n cross n plus 1, and obviously then for n plus 1 cross n, both row and column can be removed, which is what our initial reducible was, right? Both row and column can be removed. And in other cases, it is not possible. Yeah. So for n cross n plus 2, it is not possible. So you can create an example. We have kind of already created, but you can create an example. You can take a 2 by 4 matrix and you can show that it is not possible. Yeah. So can you give an example for 2 by 4 or 4 by 6? That will be good to see an example, right? Yeah. Good. Or let's do 2 by 4 only. Yeah. 2 by 4. Because I mean, this method did not work doesn't mean that nothing will work, right? Right. So one has to no, yeah. Anyways, let's just do an example. One can explain it without an example, but let's just see an example that where it is not possible. Someone give me some example. 2 by 4 matrix, and both cannot be removed. Yeah. So you can just make any example. I think will work. So which row and column can we remove? None, right? You can just see if you remove this row. Oh, no. Sorry. You see, it's possible. You can remove the last row and the second column. And so it is possible, right? In this case, so let's make another one. Let's see. We should see if we might be wrong. Now we cannot, right? Yeah. Now if you remove this row, then which column will you remove? Well, none. Because if you remove this column, then you also have, then you'll get this thing. And here you cannot, I mean, here it is not regular, right? Second column doesn't have a 1, and similarly this, and similarly the other case. Yeah, you see, again, there is a 1, 1, 0, which is not a good matrix, not regular. Yeah. So for 2, so when the gap is 2, then it is not possible. When the gap is 1, then we can latch onto the square case and get the work done. It's kind of like that, right? So it's very interesting. So take some examples and play around. Yeah, that's the way. If you want to understand, you cannot just, yeah, you have to, means if you want to get more of intuition, you have to just play around with examples. Yeah. And the reasoning I've given, try to apply that reasoning. Go row by row. When you want to remove a column, go row by row and see which column is not used and just remove it and see if it's working. Yeah. Okay. So that's what I wanted to do. This was a good question. Basically, this question was a real question. That question which I initially asked in the test was just yeah, it's very, very special. version of it. And then in the middle, we had some other variant. I think it's good. Yeah, just some combinatorics on matrix arrays, basically. Okay, so let's stop here. So next time we will. Yeah. So is Saturday? So we want to shift the class to Saturday instead of Wednesday.